So here are a few miscellaneous points. Now the thing about these miscellaneous points is there was a question, for example, from the second point in JEE Advanced 2015 paper 2, where they directly used this property to solve a question. The thing is, they are conceptual, they are based on some sort of a concept, but they are not really something that you can actually fit under some subtopic and discuss a lot of theory around them. They are just few bits that you need to just remember. So the thing with these miscellaneous things are, it's really disorienting, because it makes you feel as if you have not learned enough about the subject, and there might be something more miscellaneous that's missing. But for now, I would like to tell you that don't let such thoughts enter your head. Whatever is important, whatever has not been covered, I'm covering that right now under this miscellaneous thing. I don't think anything other than all of this and the required concepts that I've already taught you, you would need to actually separately sit down and study, right? So just focus on these 3 points without going into a lot of proof as to why they are valid. Let's just look at them and try to form an explanation about them. So the first point says, if I have two vectors a bar and b bar, and these two are non-collinear, then any vector, you have vector a bar and b bar, and they have to be non-collinear, right? This is very, very important. These two have to be non-collinear. So if these two are non-collinear vectors, then any vector r bar coplanar with a bar and b bar can be expressed as a unique combination of a bar and b bar in this form, x a bar plus y b bar. Let's see what the statement means. I will explain you the statement, and you can reread the statement and understand it yourself. You have a plane, right? A bar and b bar are two vectors in this plane. Remember, two vectors are always coplanar, right? Three vectors might or might not be coplanar depending upon the property that we have seen before, but two vectors are always coplanar. Just like from 2 lines, from 2 points, you will always have a line passing through. Similarly, from 2 vectors, you will always have a plane passing through. So 2 vectors are always coplanar. So now, if these 2 vectors are non-collinear, right? So for example, if you don't have a and b along the same straight line, right? They might look something like this. You have this a bar like this and b bar like this. They are not in the same direction, right? So they are non-collinear. Then any vector r bar coplanar with a bar and b bar can be expressed as a unique combination of x a bar and y b bar. So if I take any other vector in the same plane r bar, then I can write r bar as some x a bar plus y b bar, and it's a unique combination. So for example, if your r bar is 2a bar plus 3b bar, it will only be 2a bar and 3b bar. It can't be anything else, right? The moment you change any of these numbers or the order or whatever, you will end up getting some other vector in the same plane, right? You will end up getting some other vector in the same plane. So what I mean to say is, first of all, your two vectors, these two vectors have to be non-collinear, right? They shouldn't be in the same straight line. If they are non-collinear, then any vector in this plane can be expressed as a unique combination of this form, right? I can use these two. Just multiply this with some vector, just multiply the other with some other vector, and I keep changing this lambda and mu, and I'll keep getting different vectors in the same plane. So I can pick up any of these vectors and I can represent them with the help of a bar and b bar, right? This was your first property. Let's move on to the second property. So the next point is on similar lines. Now instead of two vectors, if I have three vectors a bar, b bar, c bar, and these three are non-coplanar vectors, right? Your vectors a bar, b bar, c bar are non-coplanar vectors, then any vector r bar can be uniquely expressed as a linear combination of these three vectors. So what is the difference between the first point and the second point? In the first point, you had two non-collinear vectors. Here you have three non-coplanar vectors. That is the first difference. The second difference is every vector r bar coplanar with a bar and b bar. Here, any vector r bar can be uniquely expressed. So that vector can be anything, right? Literally any vector. And here you can represent them using a bar and b bar only if it's coplanar with A bar and B bar, right? And here you can represent any vector as a linear combination of these three. So what it means to, this point means to say is, if I have three vectors, for example, A bar, B bar, and something like a C bar here. Now the diagram clearly shows that, okay, these three are not coplanar, right? So if I have a plane, these three don't lie in the same plane, right? They are non-coplanar. So I can take up any vector. For example, I can take up this vector R bar, and I can write R bar as some X into A bar plus some Y into B bar plus some Z into C bar. X, Y, Z are unique. Once again, what does this mean? If it's something like 2A bar plus 3B bar plus C bar, this vector that you see here, if it is something like this, then it will only be this, right? The moment I change this 2 to 1, this R bar might change to something else, right? It has to be uniquely only this 1, 3, 1, right? Your XYZ has to be, sorry, this is 2, 3, 1, right? Your XYZ has to be completely unique, right? In fact, I would like to draw your attention to something as far as this point is concerned. This point is not something that you're, okay, I agreed that you're seeing this point for the first time, but it's not that you're using this point for the first time. Can you just think and tell me how have you, or tell yourself rather, how have you been using the second point already? So in this chapter, throughout our discussions, we've already been using this point without stating this miscellaneous point, right? Where have we been using it? So the answer is your coordinate axis x, y, z. And if I take unit vectors I cap, j cap, k cap, these unit vectors are also non-coplanar, right? Obviously, this is a different plane, this is a different plane, this is a different plane, right? This one, and this one. These are three different planes. So these I, j, k are three different vectors, right? Three non-coplanar vectors. So instead of A, B, C, this I, J, K is also valid. They are also three non-coplanar vectors. So I can represent any vector as some xi plus yj plus zk. In fact, I've been doing this already, right? Where your x is called the x component, y is called the y component, z is called the z component. The moment I change any of this x, y, z, the component changes, the directional cosine changes, the vector changes, right? So they are unique. This xyz is unique. And what is this? Basically, you take any point in the three-dimensional plane and the vector which starts from the origin and goes to this point, right? That is basically your R bar, right? The vector which starts from the origin and goes to this xyz. But what have we been doing? These three vectors which are non-coplanar, I've been using a combination of these three to represent any of my general vector R bar, right? This doesn't mean that the vectors can be represented only using ijk, right? Ijk, we use ijk because it's a very simple notation, because of convenience of calculations, because ijk are perpendicular to each other. This is the reason why we use it all the time. But that doesn't mean that I can't use these three. Let this be some A cap, B cap, C cap, which are not at 90 degree but are non-coplanar. So if these three are non-coplanar, I can represent any R bar using these three also. I need not always go back to I, J and K, right? So this is something that I wanted you to draw your attention to. With this, let's move on to the next point. So the third point as of now might seem very confusing as to how this representation is valid. I'll explain you this point, but I would like you to know that as far as the proof of this point is concerned, we will obviously look at this proof in detail when we study the further topics in vectors, especially when we study this topic, scalar triple product. In fact, when we even study 3D geometry, when we even study planes in 3D geometry, we'll once again look at this third point. So this third point you are encountering for the first time here, you'll encounter it again here, you'll encounter it again here, right? So by the time you encounter it here, it will become very clear as to why this point is valid. But as of now, I can only ask you to accept it as it is, because the proof is combining both your matrices and the knowledge of your dot product and cross product, which I don't want to get into right now. Let us just accept this point for now, because it's one of those important points, one of those tricks where questions keep coming in JEE mains especially, where they would directly ask you to use this property. A lot of times questions have come from this. So just make sure you accept it as it is right now. So you have three vectors given in their component forms, right? So the first vector is basically your A bar, which is AI plus A1I plus A2J plus A3K, and you already know this is called the component form, right? Where A1 is the X component, A2 is the Y component, A3 is the Z component, right? Similarly, you have B in its component form and you have C in its component form. If these three are to be coplanar, so these three are vectors, right? These three are vectors. If I want to verify whether these three are in the same plane or not, for example, something like this, these are three vectors which are in the same plane. So your A bar can be this, your B bar can be this, your C bar can be this. And if I want to check whether they are actually coplanar or not, then this has to be valid. What is this? You take the X components of all the three, you take the Y components of all the three, and you take the Z components of all the three. You take the determinant of this matrix, this is CZ. What do? You take the determinant of this matrix, and this determinant has to be equal to 0. Right. I'm not at all getting into how this determinant is. Why should this arrangement be taken? Why should this determinant be 0? We will look into that later. But for now, just take the X components in the same column. Just take the Y components in the same column. Remember, don't mess up with the order. Just remember the order as it is. Take the Z components in the same column, and the determinant has to be 0, right? Determinant of this matrix has to be 0. If it is 0, then these vectors are in the same plane. If it is not 0, then one of them is just playing around. Like if it's one of them is just, something like this, it is just pointing out with some angle with respect to with respect to the plane. Even though it might so happen that two of them might just point out of this plane, this particular green plane that I've drawn, right? So ultimately, all the three will not be in the same plane if it's not equal to 0. And if they are in the same plane, then this particular arrangement and this result has to be valid. This particular determinant has to be 0. So for now, these were the miscellaneous points I wanted you to just take care of. They can't be actually fit under some subtopic specifically. So that is why I've given them as some miscellaneous things that you need to just remember. With this, we complete the introductory part of vectors. We will now move on to a few important products of vectors. Some products like scalar product, vector product, scalar triple product, vector table product, like things like these, which have some geometrical significance and also some physical significance. They are also used in physics in a lot of places. So the real part of vectors before we build up to 3D geometry is yet to come. So this was all the introduction that you needed to vectors. So with this, let's proceed with the various types of products in vectors.